the focal length of an optical system is a measure of how strongly the system converges or diverges light. For an optical system in air, it is the distance over which initially collimated rays are brought to a focus. A system with a shorter focal length has greater optical power than one with a long focal length. That is, it bends the rays more strongly, bringing them to a focus in a shorter distance. In most photography and all telescopy, where the subject is essentially infinitely far away, longer focal length leads to higher magnification and a narrower angle of view. Conversely, shorter focal length or higher optical power is associated with a wider angle of view. On the other hand, in applications such as microscopy in which magnification is achieved by bringing the object close to the lens, a shorter focal length leads to higher magnification because the subject can be brought closer to the center of projection. Thin lens approximation: for a thin lens in air, the focal length is the distance from the center of the lens to the principal foci of the lens. For a converging lens, the focal length is positive, and is the distance at which a beam of collimated light will be focused to a single spot. For a diverging lens, the focal length is negative, and is the distance to the point from which a collimated beam appears to be diverging after passing through the lens. The focal length of a thin lens can be determined by using it to form an image of a distant light source on a screen. The lens is moved until a sharp image is formed on the screen. The focal length f is then given by where u is the distance between the light source and the lens, and v is the distance between the lens and the screen. General optical systems. For a thick lens, or an imaging system consisting of several lenses and/or mirrors, the focal length is often called the effective focal length. To distinguish it from other commonly used parameters, front focal length or front focal distance is the distance from the front focal point of the system to the vertex of the first optical surface. Back focal length or back focal distance is the distance from the vertex of the last optical surface of the system to the rear focal point. For an optical system in air, the effective focal length gives the distance from the front and rear principal planes to the corresponding focal points. If the surrounding medium is not air, then the distance is multiplied by the refractive index of the medium. Some authors call these distances the front-rear focal lengths, distinguishing them from the front-rear focal distances, defined above. In general, the focal length or EFL is the value that describes the ability of the optical system to focus light, and is the value used to calculate the magnification of the system. The other parameters are used in determining where an image will be formed for a given object position. For the case of a lens of thickness d in air, and surfaces with radii of curvature 1 and 2, the effective focal length f is given by where n is the refractive index of the lens medium. The quantity 1 per Fahrenheit is also known as the optical power of the lens. The corresponding front focal distance is and the back focal distance. In the sign convention used here, the value of A1 will be positive if the first lens surface is convex, and negative if it is concave. The value of A2 is positive if the second surface is concave, and negative if convex. Note that sign conventions vary between different authors, which results in different forms of these equations depending on the convention used. For a spherically curved mirror in air, the magnitude of the focal length is equal to the radius of curvature of the mirror divided by 2. The focal length is positive for a concave mirror, and negative for a convex mirror. In the sign convention used in optical design, a concave mirror has negative radius of curvature, so, where is the radius of curvature of the mirror's surface? See radius of curvature for more information on the sign convention for radius of curvature used here. In photography, camera lens focal lengths are usually specified in millimeters, but some older lenses are marked in centimeters or inches. Focal length and field of view of a lens are inversely proportional. For a standard rectilinear lens, FOV equals 2 arctan, where x is the diagonal of the film. When a photographic lens is set to infinity, its rear nodal point is separated from the sensor or film, at the focal plane, by the lens's focal length. Objects far away from the camera then produce sharp images on the sensor or film, which is also at the image plane. To render closer objects in sharp focus, the lens must be adjusted to increase the distance between the rear nodal point and the film, to put the film at the image plane. The focal length, the distance from the front nodal point to the object to photograph, and the distance from the rear nodal point to the image plane are then related by. As is decreased, must be increased. For example, consider a normal lens for a 35 mm camera with a focal length of. To focus a distant object, the rear nodal point of the lens must be located a distance from the image plane. To focus an object 1 am away, the lens must be moved 2.6 am farther away from the image plane. 2. The focal length of a lens determines the magnification at which it images distant objects. It is equal to the distance between the image plane and a pinhole that images distant objects the same size as the lens in question. For rectilinear lenses, the imaging of distant objects is well modeled as a pinhole camera model. This model leads to the simple geometric model that photographers use for computing the angle of view of a camera. In this case, the angle of view depends only on the ratio of focal length to film size. In general, the angle of view depends also on the distortion. A lens with a focal length about equal to the diagonal size of the film or sensor format is known as a normal lens. Its angle of view is similar to the angle subtended by a large enough print viewed at a typical viewing distance of the print diagonal, which therefore yields a normal perspective when viewing the print. This angle of view is about 53 degrees diagonally. For full-frame 35 mm format cameras, the diagonal is 43 mm and a typical normal lens has a 50 mm focal length. A lens with a focal length shorter than normal is often referred to as a wide-angle lens, while a lens significantly longer than normal may be referred to as a telephoto lens. Technically, long focal length lenses are only telephoto if the focal length is longer than the physical length of the lens, but the term is often used to describe any long focal length lens. Due to the popularity of the 35 mm standard, camera lens combinations are often described in terms of their 35 mm equivalent focal length, that is, the focal length of a lens that would have the same angle of view, or field of view, if used on a full-frame 35 mm camera. Use of a 35 mm equivalent focal length is particularly common with digital cameras, which often use sensors smaller than 35 mm film, and so require correspondingly shorter focal lengths to achieve a given angle of view, by a factor known as the crop factor. See also, depth of field, f-number or focal ratio, diopter, focus, references.